This is the list of operators that we have seen so far. List of the operators associated with spin. Right? These are the list of operators associated with spin. We have an operator corresponding to the z component of spin. We have an operator corresponding to the x component of spin. Another one corresponding to the y component of spin. Right? The operator corresponding to z component of spin, I think we had seen in one of our previous classes. I think we discussed it in the classroom, so there may not be a video of it. So what we did was, we said that any operator can be written in this form. It's sum over a prime lambda a prime. Okay. In this case, there are just two eigenvalues, plus h bar by 2 and minus h bar by 2. So we have plus h bar by 2 and the projection operator, here, and minus h bar by 2 and the projection operator ket minus bra minus here. Right? That will give you this sz operator. And this lambda a prime we said was the projection operator. It was of the form ket a prime, bra a prime. And in the last couple of classes, we have been discussing Sx and Sy, their eigenkets and the operators themselves. And we have written these operators in terms of the eigenkets of Sz, eigenkets and eigenbras of Sz. All right. And we saw that Sy has complex numbers appearing inside. Right. So when you take the matrix elements of Sy, then there will be complex numbers. Now we also had the non-Hermitian operators called ladder operators. We defined also in one of our previous classes, I think in the classroom, we defined this S plus operator, which is defined as H bar ket plus bra minus, and S minus is H bar ket minus bra plus. Okay. Now the speciality of this operator is that this is called the raising operator and this the lowering operator. So we have got raising and lowering. All right. So let's just see why this is called the raising operator. Suppose let's look at the action of S plus on ket minus. Right. I'll just give this as an example and then we'll go to the next part. Suppose S plus acts on ket minus. Right. So this is equal to, there's an H bar here, ket plus bra minus acting on ket minus. All right. But this is equal to 1 by orthogonality or orthonormality. Okay. So this is equal to H bar ket plus. So we started with a state ket minus with eigenvalue minus h bar by 2 with eigenvalue of sz equal to minus h bar by 2. When we acted s plus on it, we reached a state ket plus with eigenvalue plus h bar by 2. Right? Ket plus is a state with eigenvalue plus h bar by 2 for the operator sz. Okay. So this means that the eigenvalue has gone from minus h bar by 2 to plus h bar by 2. It has been raised by h bar, right? It has been raised or it has increased by unit of h bar. Okay, this is why we say that this is the raising operator. Similarly, we can see that this operator lowers the eigenvalue of sz, all right? So that's why it's called the lowering operator, and together they are called the ladder operators, right? So these are the operators that we have discussed so far. Okay. Now, the Hermitian operators S plus minus, okay, the ladder operators can be written in terms of Sx and Sy. I think we had mentioned it before, but now we can show that this is true. We can write S plus is equal to Sx plus Isy. Similarly, S minus is equal to Sx minus Isy. All right. This can be easily checked because we have got S plus here, we have got S minus here, we have got Sx and Sy here. So we can check this. For an example, let's just check Sx plus Isy. All right, so we see that there's an h bar by 2 here. All right, so we can write h bar by 2 common outside. Okay, and Sx is ket plus bar minus plus ket minus bar plus. Okay, now what is Isy? Isy, here there's minus I, so when I multiply it with I get 1, and this becomes ket plus bar minus, and there's an I here, so if I multiply by I, it becomes a minus 1 and minus ket minus bra plus. Okay, so we see that these two terms, right, these two terms are negative of each other. So when we add, we'll get the zero operator, and this becomes h bar by 2 multiplied by twice ket plus bar minus. Okay, or this is equal to h bar ket plus bar minus, which is exactly equal to s plus. All right. In the same way, we can show that Sx minus Isy is S minus, right? The lowering operator. That can be easily shown. Let's now look at some of the important properties, or at least one or two of the important properties of these operators. Right? So these operators Sx, Sy together with Sz, these operators, all right, they can be readily shown to satisfy the commutation relations. Commutator of Si with Sj is equal to I epsilon ijk h bar sk, right? And the anti-commutation relations Si with Sj equal to 1 by 2 h bar square delta ij. All right. So here this epsilon ijk is a Levi-Civita symbol, and it is defined like this. All right. So this is completely antisymmetric in all its indices. So if I interchange any two indices, I'll get an extra minus sign. It's completely antisymmetric. All right. So this means that this is defined like this: epsilon 1, 2, 3 is 1, and it's completely antisymmetric, right? Which means that epsilon 2, 1, 3 is minus 1. It also means that epsilon 2, 3, 1 is plus 1, etc. Right? So we see that if these are the cyclic permutations of 1, 2, 3, then we get plus 1, otherwise it's minus 1. Or 0, it could be 0 if any two indices are equal. Right? If any two indices are equal, this is equal to 0 because of antisymmetry. Okay, so this is the simple and important Levi-Civita symbol. We have used it for defining cross product before, I think. Right? So just remember that it's completely antisymmetric about its indices, which means that if there are any two indices equal, right, this symbol will give you a value of 0. If if there are cyclic permutations of 1, 2, 3, it will be 1, and what is non-cyclic permutations, right? Other permutations will give you minus 1. This is the Levi-Civita symbol, right? So let's check what this actually says. We can, for example, write S1 as Sx, or we can define Sx as S1, Sy as S2, and Sz as S3. Okay, in this notation, let's write, if you want, S1 with S2, which is nothing but Sx with Sy. Right? This says that it is equal to I h bar epsilon 1 2 k, because I have 1 and 2 here. This means that this, so the idea is that I've got I and j here, and the first two indices of the Levi-Civita are I and j. Okay, so here I have S1 and S2. So the first two indices are fixed from the left side. It is epsilon 1 2. Third, there's a dummy index k, which is summed over all the possible values. This is just the Einstein summation convention that we are using, which means that repeated indices are to be summed over unless otherwise specified. So these have to be summed over. Okay, so this means that epsilon, so you can sum over all values of k, which means that there's k equal to 1, right? But epsilon 1 to 1 is 0 because two values are repeating. K is equal to 2 also gives a 0. Okay, because epsilon 1 to 0, the only non-zero value corresponds to k equal to 3. Right? So the only non-zero term in this whole summation corresponds to epsilon 1 to 3. So this is I h bar epsilon 1 to 3 S3. And epsilon 1 to 3 is 1. So you see that it is I h bar S3. In other words, we are writing the commutation relations like this. Sx with Sy is I h bar S3. So that's what it means. Okay. What does this commutator mean? What does this commutator mean? All right. We'll see what this commutator means. Okay. So I think I should have said that earlier, but that's all right. We'll see. All right. And we also have these anti-commutation relations, which say that this is a different bracket. Okay, we use a curly bracket for the anti-commutator, which says that Si with Sj is half h bar square delta ij. Delta ij is the familiar Kronecker delta. Right. That's one of the familiar symbols. Okay. Kronecker delta. So if I and j are equal, this is 1. If I and j are not equal, this is 0. All right. Okay, so I think I should tell you what a commutator means. All right, a commutator of Si with Sj, or let's say a commutator of A with B, right? A with B, this is defined as AB minus BA. So you multiply these operators in different order, opposite orders, and then subtract them. This is the commutator. So when we defined operators and we talked about operator multiplications, we said that AB is not in general equal to BA. You might have already seen this in the case of matrices. If you multiply two matrices in a particular order, right, the multiplication in the opposite order need not be the same. Okay, they could be different. Okay, so this actually tells us that the difference, this commutator stands for the difference of these operators multiplied in opposite orders. Right? That's the commutator. Anti-commutator means you are just adding these operators in opposite orders. This is AB plus BA. That's the anti-commutator. Right? So here Si with Sj means Si Sj minus Sj Si. So when I said Sx with Sy, this means this is equal to Sx Sy minus Sy Sx. Alright. Okay, I think that's clear. Oh, I had the definitions here. Okay, the commutator, the square bracket means commutator of A and B. Commutator of two operators means we just multiply the operators in opposite orders and subtract. Right? This is the commutator. And the anti-commutator is again you multiply the operators in opposite orders and then you add them. Alright, and we make use of the totally antisymmetric symbol epsilon ijk, which has the value plus 1 for epsilon 1, 2, 3, and any cyclic permutation of indices, the value minus 1 for epsilon 2, 1, 3, and any cyclic permutation of indices. So cyclic permutation from 2, 1, 3. Okay, all will give you minus 1. And the value 0 when any two indices are the same. So you just have to remember that epsilon 1, 2, 3 is equal to 1. Right? That's the only thing that you need to remember. You also need to remember that it's completely antisymmetric. So we can find every other value starting from here. Right? We can find every other value starting from here. Right? So for example, I see that epsilon 2, 1, 3 has to be equal to minus 1 because it's completely antisymmetric. So if I interchange any two indices, I should get a minus value. Right? Now I could interchange it once again, epsilon 2, 3, 1. Right? Then again I get an extra minus sign, but already I had a minus sign here, so this is 1. Right? So we see that epsilon 1, 2, 3, epsilon 2, 3, 1, epsilon 3, 1, 2 are all plus 1. Okay. All right. Now, we also make use of the implied summation convention or Einstein's summation convention. That is the assumption that we perform a summation over any pair of repeated indices. So if you have something like epsilon I jk sk, this means epsilon I j1 s1 plus epsilon I j2 s2 plus epsilon I j3 s3. This is what it means. Okay, you have to sum over all the values of k, all the possible values of k, right? These were the computational relations. Si with Sj is equal to I h bar epsilon I j k sk commutation relation, right? So I think we shall check the commutation relations here. Okay, I'll check one. I'll just check one. This means that Sx with Sy is equal to I h bar Sz. Okay, because we calculated this thing and we saw that it's IH bar Sz. We can actually calculate that from here. Okay, we can actually calculate that from here. First, let's find this is Sx Sy minus Sy Sx. So let's first find Sx Sy using this operator. So, right, what is Sx Sy? So Sx Sy is, this is h bar square divided by 4. I have just multiplied these things. Okay. And what else do I have? I have to multiply. I have to take all combinations. Okay, this is ket plus bra minus, okay, ket plus bra minus. And if I multiply it with this, right, in Sx Sy, we see that this is actually equal to 0 because we have got a bra minus ket plus bracket. So these are orthonormal state and this is 0, right? So the only non-zero multiplication is this, and there's an I here, so I shouldn't drop the I here. This is I, okay, and ket plus bra minus multiplied by ket minus bra plus. Okay, let me write it here. We have got ket plus bra minus multiplied by ket minus bra plus. Okay, now by associative axiom and orthonormality, this is equal to 1. So I have got I multiplied by ket plus bra plus. Okay, in this multiplication, we also have one more multiplication here. We have to multiply these two and these two. Right? So we have got a bra plus here. So it combines with this bra plus to give 1. So it gives a non-zero. It gives a non-zero contribution. So let's look at this multiplication. I've got a minus I here. Okay. And ket minus bra plus from here. And I've got a bra plus, sorry, ket plus bra minus from here. Again, by associative axiom, this is 1. Right, so I can take this as 1 and this is equal to minus I ket minus bra minus. Okay, now this is just Sx Sy. We also need to find Sy Sx, right? So we see that this is equal to h bar square divided by 4. Now we have to take each term from here and multiply with this, right? We see that this multiplication is 0 because there is a bra minus here. It combines with ket plus and that goes to 0. right? So the non-zero multiplication of this term is with this, right? And we have got a minus I here. This is minus I, ket plus, okay, bra minus, and from here ket minus bra plus. This is 1 by orthonormality and associative axiom. So this is 1, and we have got minus I multiplied by ket plus bra plus. Yes. Now let's check the multiplication of this term. This is the only non-zero multiplication here because this multiplication is 0. Okay. So this gives plus I, there's an I here, ket minus bra plus, here I have got ket plus bra minus, okay, and this is equal to 1, right? So we see that Sy Sx is equal to h bar square divided by 4. Here I have got minus I ket plus bra plus I ket minus bra minus, okay, all right. Now, what do we need to find? We need to find Sx Sy minus Sy Sx. So we have to subtract this from this, right? We have to subtract this thing from this thing, right? Equation 1 minus 2. Let's see, there's this h bar square by divided by 4 common outside. So I can take this, gives you, right here, h bar square divided by 4. There's also an I appearing here. All right, should I take this I outside? Maybe not. Okay, we'll do that in the end. So I've got I ket plus bar plus here, and I've got minus I ket plus bar plus. Okay, but we are subtracting them, so this becomes 2I ket plus bar plus. Okay, so these two terms we have subtracted. Now we have got minus ket minus bra minus here, and plus I ket minus bra minus. Okay, we are subtracting, so this will become a minus, and I get minus 2I ket minus bra minus. Okay, I've just subtracted these terms. All right, now this 2I can be pulled out, so this is h bar square divided by 2, or I h bar square divided by 2, and we have got here ket plus bra plus minus ket minus bra minus. Okay, all right. Now I see that we can write this as, this is equal to, let me just put I h bar outside, and let me take h bar divided by 2 inside, right? Or we can write like this, I h bar multiplied by h bar divided by 2 ket plus bra plus minus ket minus bra minus. What is this? This is exactly the Sz. This is exactly Sz that we have here. H bar by 2 ket plus bra plus minus ket minus bra minus. Okay, so what we have found here is that Sx Sy minus Sy Sx is I h bar Sz, exactly as predicted by this equation. Exactly as predicted by this equation, Si with Sj is equal to I h bar epsilon ijk sk. We have only checked one of these commutational relations and it works. Okay, actually, as an exercise, you can check all of the commutational relations and show that this relation is actually correct. That you can check every possible commutational relations, right, and show that this relation actually works. Right, you can find Sx with Sy, Sx with Sz, Sz with Sx, and Sz with Sy, and see if this gives the correct result. Right? So convince yourselves that the commutational relations can be summarized using the Levi-Civita symbol in this form. Right? So or we can say Sx with Sy is equal to I h bar Sz. Okay. Now these commutational relations Si with Sj is equal to I h bar epsilon ijk sk. Okay. These commutational relations are known as the angular momentum commutational relations. So we'll see that these are actually the simplest realization of the angular momentum commutational relations. So its significance will be discussed later. So all the properties, everything related to these operators can be obtained, okay, can be derived if these commutational relations are known. Right? So we can start with the commutational relations of angular momentum operators, for example, and then derive all the possible eigenvalues, etc. But this we'll be seeing when we discuss angular momentum algebra. Okay. For here, we have just seen that these spin operators that we have constructed, they obey a particular set of commutational relations given like this. Okay. Now, the anti-commutational relations are a special property of the spin half systems. Right? So the anti-commutational relations said this, we have got Si with Sj is equal to half h bar square delta ij. It was half h bar square delta ij. All right. Now we could also check this. All right. So this actually means that the anticommutator of Sx with Sy is 0. If these are different, it's 0 because of this Kronecker delta here. Okay, you have to check this. All right, I leave it as an exercise for you to check. Just as we checked the commutator, you can check these anticommutators also. Okay. All right. So let's, for example, what does this mean? Suppose I and j are x. Suppose we are talking about the same operators. Okay, this means that Sx with Sx is equal to half h bar square delta ij. Delta ij is 1 in this case. Right? So Sx with Sx is half h bar square. And actually there's an identity operator here. Right? So if you are thinking of this as matrices, this is also a matrix here, the identity matrix. So there's an identity operator here, but we don't write that explicitly. All right. Okay, so these are the anti-commutation relations. Now we can also define the operator S dot S or S square for short. Right? So this is S square or S vector square. This is equal to Sx square plus Sy square plus Sz square. All right. Now this is the definition for the square of the spin. All right. So you can call it as S square or S vector square. Right? Or S vector dot S vector. Now this can be found using this anti-commutation relation. So from here you see that this is Sx Sx plus Sx Sx by the definition of anti-commutation relation. So this means that twice Sx square is equal to half h bar square. Okay, there's identity operator there. We are not writing it explicitly. So this means that Sx square is h bar square divided by 4. Okay. Similarly, Sy square is also h bar square divided by 4 by the anti-commutation relations, and Sz square is also h bar square divided by 4, again by the anti-commutation relations. Okay. So what is S vector dot S vector or S square or S vector square? S vector square is Sx square plus Sy square plus Sz square, which is equal to 1 by 4 h bar square plus 1 by 4 h bar square plus 1 by 4 h bar square. I have just used the anti-commutation relations. This is 3 divided by 4 h bar square. Okay, it has to be h bar here. So it's 3 by 4 h bar square. Remember, there's an identity operator here. So this means that S square is actually proportional to the identity operator. It's proportional to S square is proportional to identity operator. It's proportional to the identity operator. Okay, so I haven't written it here, but remember that the identity operator is always there. Similarly, we see that every component, all right, we saw that Sx with Sy, the commutation is not 0. This is not equal to 0. Instead, let's just say that this is not equal to 0. All right. But if you look at the commutation of S square with Sx, this has to be equal to 0. Why is that? Because S square is 3 by 4 h bar square, which is a number. So this is the commutator of identity operator with Sx. Now identity operator commutes with every operator, so this has to be equal to 0. Okay, because Isx, identity operator multiplied by Sx, has to be equal to Sxi by definition of identity operator. Okay, it does not change anything. All right. So we see that Sx, Sy, and Sz commute with S square. All right. This fact will turn out to be important later on. Okay, that's why we are mentioning it here. So when we say that two operators commute, when I say that A and B commute, what I mean is the commutator A comma B is equal to 0. Right. So here we are actually saying that Sx, Sy, and Sz, all of them commute with S square. All of them commute with S square. All right. So again, we'll be discussing these things in chapter 3. Okay. So for spin higher than a half, S square is no longer a multiple of the identity operator. This is only a feature for spin half systems. For higher spins, it's no longer a multiple of the identity operator, but this relation can still be shown to hold. Right? We can show that this relation actually holds even for higher spins other than half spin cases. All right. Here it was easy to prove. Here it was just easy to prove because it's proportional to the identity operator. Before concluding, let's just look at the matrix representation of this operator. So, right, so I'll give you the matrix representation of Sx, all right, in the basis of eigenkets of the Sz operator. So these are the basis vectors I have. Right? This is the base set of vectors. Right? These are the eigenkets of the Hermitian operator Sz, and we have said that the eigenkets of any Hermitian operator can be used as basis. So let's look at the matrix representation of Sx in this basis. All right. So I leave it as an exercise for you to find Sy. I think we have already done Sz before. Sz was just a diagonal matrix 1, 0, 0, minus 1. All right. Okay. Now I ask you to find Sy. I'll just calculate the matrix elements for Sx. Right. Let's look at the matrix representation for Sx. How do we do this? We see that the matrix elements can be written like this. We have got Sx. This is ket plus, ket minus, bra plus, bra minus. Right? What's the element here? It's this combination, bra plus Sx ket plus. Okay, this is bra plus Sx ket plus. This is bra plus Sx ket minus, bra plus Sx ket minus. All right. Here I have got bra minus Sx ket plus, and I have got bra minus Sx ket minus. Well, these are the matrix elements. Now we can actually calculate these matrix elements because we know that Sx is equal to, we had Sx as h bar by 2, h bar by 2, and then multiplied by, we had ket plus, bra minus, plus, bra ket minus, bra plus. Okay, this was the Sx operator that we constructed, okay, or that we found. So let's find each matrix elements now. Here, this matrix element would be bra plus Sx ket plus. Okay, so we push a bra plus from the left. Right, we push a bra plus from the left and a ket plus from the right. Right, so this is h bar by 2, which is a number. I have a bra plus here, and inside I have got bra plus ket minus plus ket minus bra plus. Okay, and I have got, what do I have here? I have got a ket plus here also. Okay, so we see that this ket plus with this bra, so this bra plus with this ket plus is 1. That's fine, right? But this bra minus with this ket plus goes to 0. Right? So this term is 0. The first contribution is 0. Similarly, you see that this bra plus acting on this ket minus, that is also 0. Okay, so we see that all these terms are 0, and the first matrix element is actually 0. Right? We could find this matrix element plus Sx minus. Right? So let me just write it here, plus Sx minus. Here I have got a minus. Right? So again I see that this this is bra plus, this is ket plus, which is equal to 1. Here I have got bra minus and ket minus, which is also equal to 1. Right? So this term will survive. There's one more term, bra plus ket minus. This term is also 0. Right? So this term does not contribute. So only contribution is h bar by 2, okay, bra plus ket plus bra minus ket minus, which is equal to 1. Okay, bra plus ket plus is 1, bra minus ket minus is 1. So this is simply h bar divided by 2. Okay. Similarly, we can find this matrix element bra minus Sx ket plus. Okay, let's do that here again. Bra minus Sx ket plus. So I'll have a bra minus here and a ket plus here. All right. Now what is this? Let's look at each term. This is bra minus ket plus. So that term is going to 0. Bra minus ket plus. That's 0. Orthogonality. Okay. Let's look at the second term directly. Bra minus ket minus. That is 1. And bra plus ket plus is also 1. Okay, so this is equal to 1, and I get this also is equal to h bar by 2. This is also equal to h bar divided by 2. Okay. Similarly, we have got one more matrix element left. This is bra minus Sx ket minus. Right, you can see that this is also equal to 0. Right, this is also equal to 0 because this bra minus from left will kill this term, and this bra minus from here, that will kill this term also. Right, so both these terms are 0. So we see that the matrix elements, or we can say that the Sx operator can be represented by the matrix h bar divided by 2. I have taken h bar divided by 2 common outside, 0, 1, 1, 0. Right. Okay, so in the same way, you can find the matrix representations of Sy and Sz. Right, Sz is a diagonal matrix as we have seen, and you will see that Sy is equal to, this is a complex matrix, and this is the complex matrix with elements h bar divided by 2 multiplied by 0 minus I and I 0. right? And similarly, you can find that Sz is equal to 1, 0, 0, minus 1, all right? And okay, these matrices here, so if except for this factor h bar by 2, the matrices appearing here have a special name. They are called the Pauli spin matrices. So I also have an h bar by 2 here, right? So these are called the Pauli spin matrices, which are denoted as sigma x, sigma y, and sigma z, right? So more of these things we'll be discussing when we go through the angular momentum algebra, okay? Okay, so what did we do so far? When we discussed the spin half systems, what we did is that we wrote the kets Sx plus minus, right? We also found expressions for the ket Sy plus minus. We also found expressions for the operators Sx, Sy, and Sz. Obviously, we talked about S plus and S minus, the ladder operators. Okay. In the end, we also looked at this matrix representations of these operators. All right. And we introduced what's called as the Pauli spin matrices. At least we mentioned what's called as the Pauli spin matrices. These are called the sigma x, sigma y, sigma z. These are called the Pauli spin matrices. Pauli spin matrices, right? Named after Wolfgang Pauli. Right? And then we also discussed, importantly, we talked about the commutation relations. We talked about commutation and or commutators. We talked about commutators and anti-commutators. Okay, so these are the things that we discussed in the case of spin half systems. So what we have done here is actually we already discussed the basic postulates, some of the basic postulates of quantum mechanics. We talked about measurements, etc. We have actually shown in this in the previous classes and this class we have actually shown how this mathematics actually works in the case of spin. All right. So with that, I'll conclude this session of the discussion on spin half systems for now. We'll be returning to spin half systems over and over again, right? So thank you for now.